Before you watch this video, make sure that you are watching the other video that's on my playlist on my YouTube channel to make sure you have a good understanding of what base E is all about. That video is pretty extensive in terms of understanding the derivation or the natural occurring letter that or number that is E. And so make sure you watch that first before you go on this video. There was a lot talked about in that video, and at some points I think he went probably too far for what we need to do in Algebra 2. However, what I do think is that he did a very good job at explaining where E comes from. Realistically, in our class, I'm more worried about the application of E and what we can do with it versus actually understanding kind of where does it come from, how is it derived, or anything of that nature. And so while that's a very, very good video, and I think it's a great jumping off point, I really want you to focus on, okay, if I understand what E is, great. If I don't have quite a good handle on it yet, that is fine too. But please make sure that you see anything on this page or on this video that you understand what I'm doing. Okay, just looking at your screen, I have a couple basics. One, it's a special number. It's kind of like pi. Pi is a special number that naturally occurs with circles. We also have the Fibonacci numbers. If you come into my room, you look at some of the posters on my wall, we can talk about the Fibonacci numbers. And E is another one of those kind of special numbers that occurs a lot in math. And so we have to look at it as a result to try and figure out what's going on. It's an irrational number, and as the other video said, it was discovered or at least learned about by Leonard Euler, and it's used a lot in higher level math. So this is just a start. I'm just giving you a little bit of an exposure on it, and then you're going to use it quite a bit in pre-calculus and calculus, and actually you saw a little bit of calculus in that video when he started talking about limits. As x approaches infinity, what's this happening with this graph? And so not that we'll talk about that a whole lot in this class, but again, it's something that's used a lot more in the path that you're going over the next couple, 3 years. First of all, you saw this already in terms of looking at creating a relationship between E and exponential. As he graphed that, and he actually graphed the E function, the E exponential function on his video. Okay, I just have it already graphed out here, and I did the same thing, where you can see it is a growth model. It still goes through 0, 1, and you can see it grows from left to right. And why is it growing from left to right? Because you know that E, the value of E is greater than 1. It's 2.7, yada, yada, yada. And so if that's the case, I know I have a growth model. I'm going to be growing from left to right. It's going to have an asymptote at y equals 0, and it's going to grow infinitely as x approaches infinity. Well, how do you graph it? Because I am going to ask you to make sure that you be able to graph these things. The nice thing is it's treated like every other parent function. There's nothing else different. I mean, no matter what parent function we're talking about, realistically, it's the same thing. And so if you look in the yellow there, we have y equals e to the x minus 2 plus 4. Hey, that thing tells me I move the parent function, that y equals e to the x, 2 units to the right, because I have that minus 2 inside the function, and 4 units up, because the 4 is on the outside. And similarly, if I have e to the x plus 5 minus 1, that's going to tell me I moved that parent function 5 units to the left and 1 unit down. Again, there's no tricks here. There's no rule. There's no other rules here that we have to memorize. We already have them memorized. I'm just using a new tool, a different kind of exponential, to do the same thing. And realistically, there's no way we can do this without some sort of calculator for the most part, and as well as make a table. Okay, these numbers are going to be pretty hard because that base, that E value, is already an irrational number, and so it's not going to be very nice to work with in the first place. And so make a table. Okay, make a table until you get a good-looking exponential model, and then once you do, go ahead and graph it, and you should be done with that problem. So my question is, how am I going to know if something is growth or decay? If I have y equals e to the x, and I'm actually going to write that on the board here. Okay, if I write down y equals e to the x, and I'll do it kind of towards the bottom here so you can see it a little better. If I say y equals e to the x, okay, you're always going to say, hey, this has to be a growth model, okay, because when I look at that, I know that e, the base, is going to be greater than 1, so I have something that's going to show growth. Okay, in actuality, I can also talk about what happens if the exponent, not the base, but if the exponent is negative or positive, that will also indicate growth or decay. And we'll only talk about this in relationship to the e powers, at least for now. And when I look at something, and if you look at it, what's in yellow, okay, I want to know, hey, how am I going to tell if it's growth or decay? Well, it's pretty easy. If the exponent is positive, then the model shows growth. If the exponent is negative, then the model shows decay. And so realistically, if I come with an example, if I have y equals e to the negative 4x, I think that is going to actually be something that is decay. because I have a negative value. And similarly, if I have something like y equals e to the 3x, I think that's going to be growth because I have a positive exponent. And so that's another way you can look at it in terms of understanding how to show growth and decay. This is something else we can start looking at. Now, tell me, if I look at these two, which ones are growth and which ones are decay? As you look at number one, my focus is going to be looking directly at the exponent with e. So I have e raised to the 0.5x. If I raise e to the 0.5x, I think that's positive. I think this shows growth. Okay, because of that 0.5x, it's a positive, it's going to show growth. Conversely, if I look at number two, you can see it's e raised to the negative 1.5 times x plus 2. If that's the case, I think that's a negative exponent, and so I think this shows decay. Okay, in your homework as well as the stuff going forward, if they were asking for something like that, you can always depend on looking in the power. Besides looking in the base, if you look at the power, it's also going to help you show growth or decay. Now, it's also going to ask you, how do you work with these things? If I give you an e in some sort of algebraic expression, how do you work with them? Here's the beautiful part. It doesn't change anything else from what we usually do with our exponent rules. So like in number one, we have e to the third times e squared. If that's the case, I have a base times a base, and the bases are the same. It's just like saying x cubed times x squared. If I did x cubed times x squared, that's a base times a base, and we all know that we have to add the power. So if it's e cubed times e squared, I'm going to add the powers. I think I get e to the fifth. If I look at number two, I'm taking a base divided by base. As long as those bases are exactly the same, okay, I can go ahead and use the exponent rule that if I'm dividing bases, I can subtract the powers. And so if I look at this, I really have e to the 3 minus 4, and we know that to be e to the negative 1. And we know by now that we don't leave negative exponents, so if that's the case, I'm going to say, hey, this is really 1 over e as my answer. Okay, and then finally, number three, you got to ask yourself, okay, what's on the inside? Can I distribute to 3? In this case, I can distribute to 3 because there's only existence of multiplication on the inside. So, quote unquote, I can go ahead and give that 3 to everything on the inside. So I really have 4 to the third power and e to the 2x all raised to the third power. And if that's the case, 4 to the third, 4 times 4 times 4, I believe is 64. And when I look at e to the 2x to the third, I'm taking a power to another power, and we know that rule to be multiplication. And if that's the case, I think I get e raised to the 6x. That's all I'm going to do for now. That's as simplified as I possibly can go without adding an equal sign. Now, one big thing, there's a lot of information on this screen. Okay, there's one more formula I want to add. Okay, first of all, compound interest. We learn compound interest to be. We learn compound interest to be something along the lines of A equals P times the quantity 1 plus R over N, all raised to the NT. Okay, it was a growth model talking about gaining interest over a certain number of times a year, and that was what the N stood for, whether it be monthly or bi-monthly or annually, whatever it might be. Okay, and that represented compound. Okay, but then we also have to add in what happens if we continuously compound. And what continuously compounding means, as soon as you do it, as soon as you go ahead and compound on the value that you have, boom, do it again. Okay, get the value, do it again. 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 Okay, so it's not weeks, it's not days, it's not hours, it's not minutes, it's not seconds. It's boom, 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 boom. It's continuously doing it for however long that you want it to go ahead and do. Okay, what happens when I actually do that? And even more so, what's that n value going to be? Okay, I can't go ahead and describe that with an n because there's nothing small enough to represent some kind of n value. If I use days, I have 365 as a number. That's how many times I'm going to do it. If I talk about hours or minutes or seconds, I can figure out how many of those there are in a year. But continuously, okay, there's really not an amount I can go ahead and drill down to. Okay, so instead of compounding interest once a year or every month or every week or every day, what if we continuously compound a value over a certain time period? What happens? Okay, here's a new formula for you. It's called A, which is going to be the amount still. P is still going to be the initial amount. Okay, so I know I'm going to mess up this picture here, but A, exactly the same. P, exactly the same. Okay, E is a little bit different. My rate's a little bit different. I still have time. We can actually call this the PERT formula, P-E-R-T, PERT formula. It's P times E raised to the RT. So notice that the R and the T are exponents of the E. So P is the initial amount, R is the rate, and T is still time in years. So as you look at this, let's give you an example here. Let's figure out what's going on. Okay, if I look at this, it says you deposit $4,000 in an account that pays 6% annual interest, compounded continuously. Here's your key to figure out which one you're going to use. You have a lot of different models at this point. Okay, you should know if you see compounded continuously, you know you're going to use your new formula of A equals PE to the RT. It says what's the balance after 1 year? What's it after 3 years? So if I look at this, if I want to plug in, and we'll hammer out the 1 year first, I say, okay, I want my amount, okay, after 1 year. My initial amount, well, was 4,000 times E raised to the rate times time. My rate was 0.06. That still remains as a decimal, okay, and my time is only 1 year, so I'll multiply it by 1. Now, if you take out your calculators, go ahead and calculate that. First of all, if you look on your calculator, the E function, okay, is actually, there's in a couple different spots. You can see that I have E right above the division sign. It's the second function of the division button. Okay, but then also if you're going to raise E to a power, which we are in this case, okay, you can see that E to the X is actually the third button from the top or from the bottom left on the far left column. And again, it's the second function. So when you look at this, I can go ahead and go 4,000 E raised to the 0.06 times 1, which is really 0.06. And I think I get 4,247 and 35 cents. Okay, well, what if I do it for 3 years? So I got 1 year taken care of. What if I do it for 3 years? I do amount equals 4,000 times E raised to, in this case, still 6%. I'm going to fix that E a little bit. Okay, 6% times now 3 years. So go up and go ahead and type that in. 4,000 E to the 0.06 times 3 this time. And when I do that, I have a new amount after 3 years be $4,788.87. If you relate that to what we've been doing with compounding over a certain number of times, whether it be years or days or weeks, hopefully you're seeing almost right away that this is going to be much better for you. We talked about in previous days that the more often that you compound, the better off you're going to be. So if you go boom, 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 and keep doing it over and over again, you're actually going to earn your money a lot faster and actually do very well with it. So you can see here, in only 1 year, you started with 4,000. After 1 year, you've already gained $247.35. Okay, after 3 years, you've already gained $788.87. Obviously, you're not going to find this many places like a bank because obviously they'd be paying quite a bit of money. But it is interesting to think about. If you keep doing it back to back to back to back to back, okay, that's actually it increases your amount that much more rapid. Tomorrow we'll talk more about it, try and put it all together, and hopefully you have a good understanding of what E is. Have a good night. I'll see you tomorrow.